Welcome to a new edition of the Heat Treat Podcast. Today we have Doug Puerta, CEO of Stack Metallurgical Group, and we're going to be talking about hot isostatic pressing, which is like the trending subject, the trending technology that it's on the heat treat industry. How's it going, Doug?
Very good. Thank you for having me.
So, Doug, this hot isostatic pressing or HIP or however you want to call it has been like the trending topic, and all commercial heat treaters are talking about this new technology because we're not using furnaces on this type of heat treatment. We're using a press, and most guys are familiar with furnaces and tempers and carburizers and vacuum furnaces and pit furnaces. But when it comes to a press, it's a totally different animal. So I'm super happy that today we're going to have you explaining the process, the machine, the key things to consider, and why it's such a disrupting technology to the market. So before we start, Doug, can you tell us who Doug Puerta is, about Stack Metallurgical, the group itself? I know that you have several locations around the States. Just give us a brief introduction about your background and the company you work for.
Absolutely. Yeah, thank you. So Doug Puerta is the son of Ralph Puerta, and Ralph Puerta is a heat treater back in Pennsylvania. So I started in the heat treat business with my dad in 1982. So I'm quite sure I was legally too young to be working at the time. Nonetheless, I was helping him out in his shop in Pennsylvania. That was Pennsylvania Metallurgical, and he now has a smaller, actually not so small anymore, shop in Percy called Vacuum Brews. So I worked with him until I was in my 20s, and I spent a couple of decades in materials testing. So I've really spent almost my entire career in services. People send us things, and we send them back and tell them, or provide services or results or things like that. I got to know the Stack business when I moved to Oregon in 2008. I got to know Nels Plow, who's the technical director of Stack, and I got to know Dave and Dan Ederer, who are our owners. And yeah, we became friends over the years, and we talked at times about coming together and finding a role for me in the business. And then the stars aligned in 2018. And yeah, I joined Stack at that time as CEO, and we set out a pretty ambitious growth path from that point forward.
And tell us a little bit about Stack. How many plants do you have? What is like the core business? Because I know you have a diversity of processes.
Yeah, so Stack has 4 facilities in the Northwest. Our largest facility is in Portland. That's where I sit most days. That's Stack Metallurgical Services. We have a facility in Spokane, Washington, which is very similar to our Portland facility, very similar capabilities, just a bit of a smaller footprint. We have a facility in Salt Lake City, Utah, which is aerospace aluminum processing. So strictly aluminum. And there, unlike other facilities, we do some chemical work as well. We do some anodizing, we do painting, FPI inspection, and then of course heat treating. And then our newest facility is Stack HIP in Albany, Oregon, which is about an hour and 20 minutes south of our facility here in Portland, and that's our HIP facility. So 4 facilities total, 110, 115 employees at this time. And yeah, a pretty wide range of services with, again, HIP being our newest addition.
And why HIPing? I mean, and we're going to talk about this today, but being a commercial heat treat company, you mentioned aluminum, LPC. Where did the market requested a new process or a new system that there are not many machines like this around? Where did Stack see the opportunity to service this market, which problem was solved, and were the suppliers asking for this process, or you just bought the machine and say, hey guys, I can do hot isostatic pressing, because that's like the big deal on commercial heat treat, when say what's first, the furnace or the contract, or in this case, did you have some RFQs before? Was the market demanding that process? Or you say, we believe the market and the industry is going to go this way, we should be prepared?
Yeah, that's a good question. And there's a few different answers. The simple answer, which I love, our owner, Dave Ederer, likes to say that we're in the business of heating up and cooling down. I mean, that's really what heat treating boils down to.
It is.
What it distills down to. And HIP, that's what HIP does. I mean, ultimately, you're heating things up and you're cooling back down again. So in some ways, it was not a great leap for us to say, well, we should get into the hot isostatic press business. Now, obviously, it's a lot more complicated than that. The HIP market is very interesting. As I mentioned, I've spent by far the majority of my career in services, testing and heat treating. At one point, before I came to Stack, I really was very eager to get into manufacturing. As a heat treater, the problem is you never have ownership. You're like almost like a daycare center. I mean, things come in and things go out again. You can never get attached because they're never yours. They're just kind of visiting and then they leave. Mm-hmm. And the thought of having ownership over making something became very interesting to me. And I spent a year working at Precision Cast Parts, which was just a wonderful experience. And I got to, be part of teams making these amazing aerospace castings. But at that time, you always have constraints in manufacturing, and there were several constraints for us because we were trying to keep up with the aerospace boom. But one of them was HIP, and it became clear that just with the trajectory that aerospace was on and the capacity available in the marketplace for HIP, that really there was room for additional capacity. And so I kept that in the back of my mind. And when I came to Stack, we talked more seriously with Dave and Dan, our owners, and talked about opportunities in HIP and what the market looked like. And what really kind of clinched it for us is, a lot of people don't know this, but Oregon has a tremendous base of aerospace manufacturing. I think in North America there are. I'm going to get this wrong probably. I think there's 5 or 6 titanium foundries, large titanium foundries. 4 of these are in Oregon. There's, okay. We looked at the market and, there's 4 of these massive titanium aerospace foundries in Oregon, but there are 0 HIP providers in Oregon. And so we said, well, gosh, Stack has been a trusted supplier here in Oregon and the Northwest for many, many years. And we consider Oregon our home, despite our footprint in Washington and Utah as well. But it kind of makes sense to us that we should look at HIP and look to provide some additional capacity to the local market. And that's kind of those 3 things combined led to us getting into the HIP business.
And myself, I'm a heat treater. I actually run a couple of companies that does heat treatment. But the impression is on this new technology, now presses, not furnaces, is that this is very capital intensive. Will be that a true statement?
That is a very true statement. Yeah, we've got a lot of furnaces around Stack, obviously, at our 4 facilities, and a lot of new furnaces. Furnaces purchased in the last 3 to 5 years. And the order of magnitude difference for a HIP unit of similar size to a heat treating furnace is quite substantial. I mean, it's 5x, 10x sort of numbers. So there is a pretty massive barrier to entry. But nonetheless, we joked around as the equipment was being installed, our first HIP unit. It looks the part. I mean, it's massive. It is massive.
I see pictures. Yeah. And it's massive, right? And one of the things I wanted to ask you is on the furnace industry, on any commercial shop or captive shop, the big names there are always ALC Holcroft, ECM, surface combustion. We got ALD. Those are like the big OEMs for furnaces. In the case of presses, hot isostatic pressings, are the OEMs American-based, Europeans? Because this is very new technology. If I would like to buy one HIP, to which convention or show should I go to be the supplier?
Yeah, that's another good question. It's interesting. It's not the same people who are making vacuum furnaces or endothermic furnaces or aluminum furnaces.
Because they're furnace builders.
Yeah.
They're not press builders.
Correct. Yeah. So even though you're heating up and cooling down, it's not the same people. The technology is much different. There are domestic producers as well as overseas producers. As we looked at our entry as our strategy to enter the market, there are HIP providers out there who have been doing this for many, many years, and they will essentially build their own presses. So they'll buy the forging, the pressure vessel, and they will buy the associated components and fabricate the press. And they do it very well. I mean, there's several of these around the U.S. and elsewhere that have been in business a long time. You know, we were not so naive to think that we could just do the same thing. You know, even though we know furnaces very, very well, we've got a wonderful team who maintains our furnaces and incredible technical knowledge to our staff. We just knew that wasn't the option for us. So we went out and really looked for more of a turnkey solution. And we identified a supplier out of Sweden called Quintus, who
you say Sweden.
Sweden, yep.
Sweden, okay.
Yeah, Quintus Technologies. And they make a number of different high pressure devices, including hot isostatic press, they do forming presses. And they were really able to offer something where, you know, they handled all the details. We just basically need to have a facility for them to install it into. And yeah, again, for us to enter the market, we felt that was the wisest strategy. It was not the most economical strategy, but it was a good partnership strategy.
And before we go on to the technicalities of the process of the machine, I would like to. This is a relatively new process. It's getting a lot of traction, a lot of attention, right? But very few people know the process itself from the beginning to the end. What happens? How do we load the press? How do we heat it? How do we put some pressure into the chamber? So I kind of have an idea, you know, having talked to some of the people which also had one of these presses. But if you could explain to the audience the heating process 101, please,
Yeah.
since this kind of new technology.
Yeah, and it's funny, you mentioned that earlier as well. And it got me thinking when we were entering or now making our announcement back in 2019. I remember at the time, Gordon the Monty was talking about every other week now, somebody's coming out talking about putting in a hip press. So yeah, it did seem to get very popular, and it seems to be gaining momentum. You know, the hip process, it's interesting. It's not terribly complicated. Of course, it is very complicated if you're building a machine. But in terms of the process itself, it's not terribly complicated. It is heat treating with the added variable pressure, which is a big deal. So we, you know, at Stack, we have bottom loading furnaces, we have horizontal furnaces. You know, the hip vessel you load from the top. So you're assembling a load, as we'll call it, much like you would do for a heat treating cycle. You've got your high temperature baskets, and you're trying to organize your parts in the baskets to maximize your loading. Your you know, different parts have different requirements based on the material, if they can touch each other, if there's sensitive spots where you can't have loading. You know, and you assemble your load, and you load it, and you place it into the hip vessel, and you close up the hip, and that's when you start to really clamp everything down, because you're going to be creating a lot of pressure inside that hip unit. Now, the different presses do that different ways.
So the seal, it's a critical part of the process. Having a good seal.
Yeah, that's very critical. And again, that's where it gets very dicey. You know, if we have of course, you can have very serious accidents with any kind of heat treating furnace. Even vacuum furnaces can have a coolant leak, and that can be catastrophic. But you know, a hip vessel with all the pressure you have inside, that's quite dangerous. So these machines nowadays are incredibly engineered. They're very safe. But yes, sealing them up properly and tightly is critical. You're talking about most hip cycles run at a pressure of about 15,000 psi, which I think, and I'll try and use both units. I think that's
fine. That's fine. I can
100 MPa, 100 MPa. And we're using argon to create that pressure. So we're using very powerful pumps to fill the chamber with argon and create pressure.
So before you create the pressure, do you pump the oxygen out?
We do. Yep, that's a good question. So the first thing you do is you'll evacuate. You'll backfill a little bit of argon, evacuate again, trying to get as low a content as oxygen in the hip unit or anything else, any contaminants in hip unit as possible. Then you'll start, you know, adding in your argon to create pressure. The cycle itself, most common cycles are 15,000 psi, which again I think is about 100 MPa. The high pressure hip units, which we can talk more about, they'll go up to 30,000 psi. They're not nearly as common, but there are materials now which specify the higher levels of pressure. And what's really interesting is if you start running the math on this, this was actually kind of fun. I was originally a chemist in school, and so years and years ago, I got introduced to this thing called the ideal gas law, which I learned in school, and I remember it, but I've never used it since school until we were looking at the HIP unit, and you can actually use this to calculate how much argon is in your HIP unit. So it was fun to finally use that, so many decades after going through college.
It
But
feels
you
good,
use
right?
that-
It feels good actually when you go like, I know that stuff.
That's it. Yeah, it was a eureka, like, oh, finally.
Yeah.
3 decades later. If you use that, you can actually calculate that at 15,000 psi, our big HIP unit, I think it fills with about 2.1 million liters of argon. So it's just, it's an amazing amount of gas. Yeah, you compare 15,000 psi with your tires in your car, which are probably 40 psi. If you go and you kick your tires, they probably feel very firm. So it's just a mind-boggling amount of gas you're putting in there.
So I want to go back one step back for a second. So we load we load the vessel, we seal it, right, and then we pump all the oxygen out, right?
Okay.
Before adding pressure, do we start putting heat into the press, or we actually pressurize with argon before taking the load to temperature?
Yeah, I believe the way we're doing it is we apply heat first and then start adding argon later on.
Okay.
Yeah, it's a little bit of a delicate dance because argon is not coming in at heat, at temperature. So I believe the way, and again, I wish I had my GM Bryce Winnie sitting next to me, because he'd be correcting me potentially. So if I'm wrong in this, I'm sorry. I've watched the process and I hear the pumps running, and I think we apply the heat first, but my back of my head, I'm thinking I'm wrong on that. So
right, okay, is because you're a metallurgist, right?
I am.
And when we add inert atmosphere to the on furnaces, is in order to prevent oxidation or a decarb from parts. For these parts, is there the parts that are going to go onto the heating process? Do we have a risk of oxidizing the parts if we go to a certain temperature, or decarburizing the parts? Would that be a risk of the process?
If we're doing it correctly, the answer is no. I mean,
Okay.
for example, the titanium parts we have coming through, they want to minimize any kind of alpha case formation. So as we're talking about this, I believe I'm realizing the correct answer is we pressurize the argon first and bring it to temperature. And now it makes sense because, again, as I said, the argon's coming in at some sort of ambient temperature. We'd be really struggling to get any uniformity if we're pumping in ambient argon as the unit was at temperature. So the answer is no. The parts, with good maintenance on your equipment, the parts come out looking beautiful. It's just like out of a nice vacuum heat treating cycle. Parts come out, shiny and clean.
And do we know which type of material do we run on the application? I mean, when we are talking about quench temperature, we go to 4041 steel type. In this case, we're talking about additive manufacturing, some other materials. What are the most common materials that we're running through the heating process?
Yeah, that's a great question. HIP is really for quality critical components.
Quality critical components, okay.
Yeah, quality critical. If the consequence of failure is very low, then you're not going to bother with a HIPing operation. But for the parts that we're seeing, which are primarily aerospace parts, the cost of a failure is very high. So in that context, you're looking at titanium components, nickel, stainless steel, aluminum. Aluminum components are not uncommon. Mm-hmm. And then there's some exotic. Occasionally we'll get requests for bronze castings or steel or. I think that's the extent of what we've seen.
Do you run 3D printing material on it?
We do, yeah. So 3D printing, even as the technology advances, it's still very difficult to print a 100% dense component. And again, a lot of these are very, very important components used in aerospace or space travel or medical implants. So the reason we're doing HIP is to drive the mechanical properties, to optimize the mechanical properties. So yeah, those parts will be HIPed as well.
Well, and this should have been my previous question, but you explained the process. We have talked about the market, the machine, but in a nutshell, when we quench and temper a part, or when we carburize a part, we want to make the part stronger, give it strength, give it case hardened. But what would be the goal when we do hot isostatic pressing? What's the goal of the material? Is there a chemical change on the material, or just a mechanical change on the material properties?
It's a, you might call it a mechanical change. Really, it's a densification process.
It's a densification process,
part.
right? Okay.
Yeah.
I don't know if I'm all right, but how I envision it is on casting materials, on cast materials, you're gonna have some pores, right? And how I think it in my mind, if that we take these materials and we go hipping, we might be able to reduce this porosity or even eliminate it. Is that kind of right assumption? But using titanium, stainless steel, nickel, or aluminum, will that be accurate?
That's exactly right.
Okay.
Yep, that's exactly the intent. I mean, I think the widest application for HIP is for casting densification. So any casting process, you're going to have some gas porosity in the casting, and you simply can't have that in any kind of quality critical casting.
Yeah, you just mentioned some minutes ago that Oregon had a bunch of foundries that were specialized on titanium, right? So are you trying to eliminate that porosity on those castings when using HIP?
That's precisely it. All the aerospace specifications actually require that for the HIP process.
Okay, and do you know when the aerospace industry started to specify that their parts should go under this process?
I don't. I know the HIP process has been used domestically, and I've seen the date before, and I believe I'll give Bodycoat credit. I believe I saw it on their website, tracing back to the start of HIP being used here in the U.S. It's been decades.
It's been decades, okay.
In terms of when it entered the specifications, I don't know if I can answer that, but certainly with the push toward more efficient engines, higher performing engines, you need to optimize material properties. And especially the HIP is a key part of that.
And especially when the cost of failure is such high, as you just mentioned, on a plane or space exploration, you name it. So I will be thrilled to know if aerospace specified that for their components, or if somebody saw that there was just like a better way to deliver parts to reduce failure. So we can leave that for the next talk. So now we talked a little bit about process applications, which is mainly on high risk components, right? No, you said high cost failure components.
Yep.
Right. And what are the considerations when installing a machine like this? Because me as a foreign expert, when you buy a furnace, there's a bunch of auxiliary things besides the building, right, that you need to take in consideration. Trays, quenching media, loading and unloading zone, exhaust system, utilities, SCADA systems, because the furnace is just only like one half of the equation, and then you get this much other considerations, which sometimes people don't budget. In the case of a heat press, which considerations should a money guy also add to the budget?
Yeah, that's a good question. It's interesting. Ironically, the building is one of the biggest considerations.
Heat treat has always been like a land business. You need to have land. You need to have some room to grow.
Yep.
So the building is one big consideration.
Yeah, and it's tricky because even as so basically it's very difficult to find a building which will allow you to place a HIP. They usually will go into a pit in the ground.
Okay, you have a pit. Okay.
So what kind of ground you have, what kind of groundwater is there. The HIP is incredibly heavy, so you need to put lots of concrete down there to support the HIP. You need a high ceiling because you're loading the HIP from the top. So I think the hook height of the crane at our facility is 31 feet off the ground.
You need a crane.
You need a crane.
You need a crane.
Big crane. Yep. And then really what you need power, a lot of electric power, and you need argon.
We didn't talk about how do we heat the press, so I'm assuming it's electrical heating.
It is electrical heating.
Okay.
Yep.
Okay.
Yeah, and it uses a lot of power between the pumps for compressing the creating the pressure in the hip unit. The heaters in the hip unit, especially for a larger size hip unit, it uses a lot of power. So you want economical power and also good access to reliable power. That's very important. And then, argon, not as much of a concern. I mean, argon travels, so it gets delivered to us. You don't need to be next to the source of argon. But there have been supply disruptions. Several years ago when the hurricane came through the Gulf and hit Houston, I believe that caused a supply interruption to argon gas. So, that's a big impact to the hip industry, among other industries.
Do we need like an exhaust system? Is there a pre or post process like tempering or washing? Do we have that on this?
Fortunately, no. So in that way, it's much cleaner than traditional heat treating. It's more similar to vacuum heat treating in that way. We can talk a bit about some of the advances in HIP, which include heat treating, combined cycles. But as HIP has been traditionally performed, it's a standalone process. The parts go back to the producer at that point. They'll do additional manufacturing operations before they go out for heat treating.
Now, we mentioned that on the process, we load the vessel, we pump oxygen out, we start heating and injecting argon into it. What's a typical cycle time? Do we vary on pressures, and how do we cool the load down? And do we purge the press before opening? Can you just conclude the process?
Yep. So total cycle time, we usually budget about 12 hours.
12 hours.
Yeah.
Okay.
That's from loading the vessel to bringing it back down to room temperature. The steps of the process, as we talked about, pressurizing the argon, bringing it to temp, doing your isostatic hold, then bringing it back down. Cooling can take place depending on the equipment, either through gas circulation or through a cooling jacket around the hip vessel.
Okay, there's a cooling jacket. Okay.
Yeah, both are pretty widely used. You have all that argon in the hip vessel as you want for the process. So you need to do something with that when you're done. You need to bring the pressure back down. So there are reclamation systems, fortunately, so you can, as long as you're confident your argon remains pure, you can reclaim the argon and reuse it. Or you can simply dump the argon, exhaust the argon in the atmosphere. It's an inert gas.
Is argon as expensive as acetylene?
Argon is...
because when we're doing low pressure carburizing and high pressure gas quenching, one of the big costs on commercial heat treating is not being able to recycle the nitrogen or helium. Nitrogen is not as expensive as helium, which helium is, but is argon as expensive, or I have no experience on it?
Yeah, because I know argon is more expensive than nitrogen, so we use nitrogen in our facility.
So it will make sense to recycle the argon.
Yeah, it does make sense. It's a non-trivial expense. I think, there's so many different units they measure argon with. CCF comes to mind, liters, all these different things. I think the total cost for a really large hip unit like we have can be several $1,000s a cycle in argon when you talk about, again, 2.1 million liters. So there's an incentive to reclaim as much of that as you can.
Go green. Everybody is trying to save energy and go into greener sources. So another question about the machine, so let's talk about maintenance. Maintenance is a big part of the cost structure of a commercial heat treat when talking about furnaces, because furnaces are self-destructive machines. We have heat, we have mechanical movements on, we have fumes. If we're doing oil quench, we have a lot of oil remains. So there's a lot of maintenance where we are heating and cooling a machine, because there's going to be some thermal shock, and the internal components are going to have a lifetime, depending if you do carbon burnouts or how often you clean your vessel. How friendly on maintenance is the heating process? Because what you just expressed right now is that we're having the machine done a thermal shock each time we do a cycle. So there should be some deterioration of the internals.
Yeah, there is. Now we're a little bit spoiled right now. So we have our hip is brand new, or it's less than a year old, so it's still nice
Okay.
and shiny, and still everything's still very
Okay.
tight. And
Take a bunch of pictures. Take a bunch of
Oh yeah,
pictures. Yeah.
we do. It's at our facility in Portland, we have all the I call them all cases still from my days
Right.
working my deck show.
IQ furnaces.
Yeah, yeah. So we have aluminum furnaces, vacuum furnaces, and yeah, I get a lot of exposure to the wear and tear and the routine maintenance required to keep them running, rebuilding hot zones, just doing the preventive maintenance. The hip unit, there's a very detailed set of procedures for maintaining the equipment. It is a ton of pressure. It's very high temperatures. And so our team there has been trained, and they have a playbook to operate to keep the unit running properly. Having said that, as you pointed out, it is destructive. I mean, you're heating up and you're cooling down. So there's a very expensive moly mantle on the inside. At some point, that'll need to be replaced. We have all the load baskets to use in any heat treat application. At some point, those need to be replaced. And it's interesting, when we do titanium, relatively speaking, is very easy. It's hipped at a much lower temperature than you'd be hipping, stainless steel or nickel alloys.
Well, what's the standard temperature for hipping titanium?
There's a range of temperatures, but they're between 1600 and 1800 degrees Fahrenheit.
Okay.
But then as you look at other alloys, then you're talking about temperatures in excess of 2000 degrees.
Okay.
Fahrenheit.
So 2000 at most, right? I will guess for stainless steel.
2000 or higher. I think we've had some. I think our vessel's capable of running up to 2300 degrees Fahrenheit.
Oh, okay, that's hot.
So we've never run it that high. But yeah, you're less eager to run those cycles because you're trying to put as much pounds in there as possible to maximize your revenue per cycle. But all those pounds on the fixturing at that high temperature, I mean, you know what happens. I mean, heat treaters know what happens. Things start to sag and distort, and they wear out.
Yeah, we didn't talk about distortion. Do we have a distortion effect after the parts have been hipped? I mean, we're not quenching, but we are adding a bunch of pressure to the material on a very high temperature. And what we want is actually to compress the part to reduce porosity. But do we experience some type of distortion on a minimal way?
I think distortion is common for any part that we would process, especially larger parts. Anytime you heat it up and cool down a part, whether it's heat treating or hip, you're going to see some movement in the part. Right. So that's why the CMM operations, the dimensional evaluations are all done at the end of the manufacturing process. There's no point in doing that after hip because then you're going to heat treat it, you're going to anneal it, or you're going to age it. It's going to move on you again. So yeah, I certainly think there is movement. I know a lot of parts are very sensitive. So the tech cards, as we call them, will say, make sure you position it in this sort of orientation. Don't stack anything on top of it. Because if you do, you're risking moving the part in a way that can't be repaired.
This is a standard practice as in other furnaces. You have to play with the load and base it on your experience, know if you can attach the parts together, if they need to be arranged in a different way or in a custom fixture. So I believe we're talking about pretty much the same as we will do on a standard heat treat furnace. Yeah.
So again, in that way, it's very familiar to a heat treater. That's maybe one of the ways it was easier for us to enter the hip market.
Yeah. And having said this, hipping is heat treated, right? Because we're actually heating and cooling stuff down. But is it a part now of CQ9 and of automotive? I know that you're more into the aerospace. Is the spec treated? Do we have to make surveys on the hip as well after we do a major maintenance for PPAP? Does the hipping process runs under the same standards of NatCap or ASM 900s revision E or which revision? Do we have to treat it like a furnace on effects of traceability, on effects of calibration of instrumentation? Are we ruled by the same standard as any furnace on hip?
Really, I think the overlap between NatCap, ISO, CQ9 is very, very high for heat treating. So whether you're doing automotive parts or medical parts or aerospace parts, the same requirements will take place in terms of calibration, uniformity, requirements for thermocouples, everything else flows through. And frankly, even if we were only doing NADCAP, or only doing ISO or anything else, I think that's a standard you want to operate to. You don't want to have to be worried about doing something only because a certain customer wants you to. You want to operate at the highest standard. I mean, it's the incremental effort in order to go from here to here is very nominal. So I think I can speak pretty confidently and say we're operating a facility that, because we're NADCAP, we also meeting requirements for CQI 9 or ISO 13485, for example.
So where do you see the future of manufacturing going? US is a lot of driven by automotive, of course, construction, of course, aerospace that took a huge hit last year with COVID because people were not getting into planes, but space exploration, now with SpaceX and Blue Origin, I mean, things are starting to roll, but there's a lot of talks about additive manufacturing, 3D printing on new materials for better shapes, and HIP actually follows into that market. Now, having said this, the 3D printing of metals and special metals for massive production is still not cost effective today, right? Maybe in 10 years. But where do you see the future of manufacturing? Right now, steel mills, steel is really expensive right now. It's very hard to get. And with this US and China trade war and not having availability to on boats, it's even more complex. But the US has a demand right now. But how do you see things are going to roll for the next 5 years? And how do you envision the next 20 years on manufacturing?
Yeah, it's interesting. Well, one, I don't think castings will go anywhere. As we were again evaluating the HIP market, we looked at Berkshire Hathaway's purchase of precision cast parts back in 2013, and Warren Buffett being behind that. And since then, I think he's been critical of the purchase and the high multiple he paid because of aerospace's collapse. But castings are not going anywhere.
Okay.
So there will always be castings, and if there's castings, you need HIP. Additive manufacturing is very interesting, and it's certainly a key market for HIP providers. Mm-hmm. So one thing we're doing is, again, we're densifying an additively manufactured component. The other thing is we can actually offer is the ability to speed up the process a bit. So if you're 3D printing a part, as you know, it's a very slow process compared to other manufacturing methods. But you can actually speed up the process a bit if you know you have a HIP vessel waiting for it afterwards. So if you go a little faster and there's a couple more defects in there and pores, you don't worry about it. The HIP will take care of that, and you get your 100% dense.
I didn't know that. Makes a lot of sense.
Yeah, so that's advantageous in that regard. One of the applications we didn't talk about is powder compaction. Powder compaction. Okay. Yeah, so that's really a very interesting process. We've done a bit of that work, but as a metallurgist, it's a process that I love. You're using powder. You're filling a shell which is designed to be essentially the component you want. You're filling it with a very tightly controlled particle size. Mm-hmm. And you're densifying it. And if you do your modeling correct, you get out a component which is near net shape. But the properties are fantastic. You have a perfectly uniform microstructure. It's uniform in all directions.
What do you think? Why is the reason 3D printing it's so innovating and not much people are talking about powder metal?
Powder metal only really makes sense on large scale. It's too easy to make a casting of something that's small. Okay, you can make a tree and put 20 of them on there and pour them all, and you've got a whole bunch of components. As you get to larger and larger components, you can't really hit a casting beyond 63 inches in diameter because there's not HIP units out there larger than 63 inches in diameter. Mm-hmm. But forgings, you can make really massive forgings, bigger and bigger forgings. But the amount of people out there who can forge really large components is small. So actually, there's some programs going now trying to develop the potential to set up they call it a Terra hip unit, I believe, a really massive hip unit, 140 inches in diameter. So you can make components which otherwise only can be manufactured by forging. So as you come back down from that and look at parts which will fit in today's hip presses, then you're dealing with 63 inches or less. And if forging is the alternative, there might be an economic advantage or a metallurgical advantage to look at this powdered metal compaction process, PM hip we call it.
Okay, so Doug, it's been great talking with you about this disrupting process. Where is it gonna go? I'm glad you mentioned that castings are gonna be here for a long time. Yeah. I hope you're right, okay? Because whenever you have castings, they're conventional heat treatment, right? And not many people like you have this type of presses. I mean, I believe there are like no more than 10 presses on the United States. Will that be a right statement?
I think there's more than that. There's quite a few different sizes.
Okay.
Again, the largest size is 63 inches in diameter. I think there's nothing bigger than that currently in North America. And there's 7 or 8 of those out there. We have one of those. But then as you get to the smaller sizes, they become more common. So if you look at the 20-inch, 30-inch diameter, I think there's probably a few dozen out there. But again, as you get larger, there's fewer and fewer.
So I believe we covered the basics on hipping. Of course, it's a very complex process. Like heat treatment, right? You never end learning, right? But do you think we missed something, or is there something else you would like to add before we close the show on the process, the market, the application, the machines?
Yeah, one of the interesting developments has been the combined cycles now. So again, traditional manufacturing process might have a hip process, and then it goes back to the casting producer or to a heat treater, and they'll do heat treating, solution, and then they'll do an aging process on a nickel alloy. So with modern hip units, you can actually combine these and do them all in the hip unit. So you'll bring it up and do the hip process and do a rapid cool and get your solution cycle as well. Then you can bring it down further and do your aging cycle. So it's very interesting. The advantage is that you are minimizing the amount of time that the part is at high temperatures. So rather than being at hip for high temperature, then in a solution process at high temperature, you can do it all in one cycle. The disadvantage is economically, you're now heat treating in a very, very expensive heat treating furnace.
You are, right?
Yeah.
Which is not meant to do that, right?
Well, yeah, yes and no. I mean, it is designed to do that. It's kind of like an airplane, as you know. Once the airplane is flying, it can fly forever. It's no wear and tear. It's very happy at that point. And so if you're leaving the hip at mostly a high temperature, it's not the hardest thing on the equipment. But yeah, because the hip is so expensive,
it is. You're gonna need to charge the hour of heat treating the same as you're charging the hour of hip, right? And I don't think it's the same price, right?
No, it's not the same price.
Right, it's like using a Ferrari to work for Uber.
That's right.
Right.
Yeah, I've not had the Ferrari driver pick me up yet.
Right. Well, but it's there if you need it.
Yeah. I need to do Uber Super XL, I guess. Right.
Well, Doug, thank you very much for sharing all this information with us, also with the audience. This is very educational, and we wish you the best success on this new innovation when you enter in this new market that has a lot of potential. Hopefully, the aerospace market continues to improve its volumes, its business for you, and I believe you're doing a great job just doing R&D, like where we're going. So I think you're giving great direction to Stack Metallurgy as a CEO, because it's always about what's next, not what's next year. It's what's in the next 20 years, how we can continue to grow. So thank you so much. Now, Doug, for the closing of the show, I mean, you're a very successful professional. You're a CEO. You have a lot of vision. You're a metallurgical engineer. You understand the heat treatment, the process, the market. You oversee 4 locations. You've been exposed to heat treat all your life. But I'm pretty sure you have had some failures, right, in your career. So some bad days, right? But to the new generations of heat treaters, what will be a personal advice or experience that you would like to share with the guys that are deciding either to apply on Facebook or apply to this company called Stack Metallurgical Group or a commercial heat treat shop? I mean, they're engineers, right? Or what would you tell the guys? What would be an advice that you would have liked to be told when you were 20 years old?
That's a wonderful question, and you're exactly right. And I've certainly had my failures, and I think the first advice is, if you're not failing, you're not trying. I mean, at some point you have to push things to the point where you fail. Now, you want to minimize the consequences of those failures, obviously, but that's going to happen. If you live a life without failure, that sounds to me like a pretty boring life. I think a big one is, we joke around at Stack that when we bring a new employee in, if we keep them for 2 or 3 months, they're probably going to be a lifer. It's just some people really, really like heat treating. They like the industrial setting. They love the big furnaces. They love being in a customer service sort of job. And I think this goes back to, when I was in college, I originally was I was getting a degree in chemistry. And boy, I hated it. I really did not like it. And at some point you need to say, if I don't like this now, I'm probably not going to like it later. And do I want to be in a career where I'm not liking it? I mean, I really like heat treating. I grew up in my dad's shop. I have great memories. Even when I was 10 or 11 and I mouthed off to the maintenance manager and he threw me in a quench tank, it's just still a great memory. I just love being around the heat treating furnaces. And so it's very rare I find myself having a long day. The time flies. I'm working with great people and great equipment, and we have great customers, and I really like it. And so I think it's very important. I know it's very hard when you're young, trying to figure out what are you going to do. Just get out there and get experience of things. Don't rush off to school thinking, I have to get a degree now, and I don't know, so I'll be a chemist or an engineer or a political science. I mean, it's very difficult. You really need to go out and try things and see what really feels good. It's got to feel good, and if it does, you're going to have a great time with it. You're going to be very happy at work and
find your passion. Whenever I talk to heat treaters or metallurgical engineers, and this is my view, not being I'm an industrial engineer, right? But when you see the industry, it's a challenging industry. It might not be trendy or sexy or fancy, but when the industry gets you, it's a very passionate industry. People speak with passion about austenite and distortion and you name it, and you see all these metallurgical guys fighting each other about opinions and theories. So I think you're totally right. It's to find your passion, and I agree 100% with you. When you get hooked, you're here for life.
Yeah. But as you agree, I'm sure you agree, it's a great community, really wonderful people. When we get back to having more face-to-face sort of events and meetings, so many people I haven't seen in many months now, and you maintain contact or email or LinkedIn or whatever forum you use, Zoom meetings. But it's a great community to be a part of.
Well, thank you very much for your time, Doug, all the way from, you said you were in Oregon, right?
Oregon.
Oregon. It was Doug Puerta, CEO of Stack Metallurgical Group. We talked today about hot isostatic pressing. Please subscribe to the channel below. We're uploading weekly podcasts with the experts on the subject about heat treat, product processes, all the innovations, the heat treat channel. Hit like. We're LinkedIn, YouTube, Spotify. If you don't want to have the video feature, we're uploading these weekly. So see you next week, Heat Treat Nation.